I'm Luke Colpo.
I'm Tyler Holcomb.
I'm Akbar Saba, and today we're going to be examining the nuclear fuel cycle.
Our problem statement was to replace Ohio University's existing power demand with an alternative source of energy, and for this we chose nuclear. We are challenged with examining the economic, environmental, and social impact of our power source, as well as the potential challenges and drawbacks in each of these fields.
Currently, all fission reactors are boiling water reactors and pressurized water reactors. So we chose the boiling water reactor over the pressurized water reactor because water can be used for a moderator, coolant, and as a reflector. Additionally, the boiling water reactor can operate at lower temperatures and pressures, involves less heat exchangers, and is just an overall simpler system.
Nuclear power generation happens in the reactor vessel. In the fuel elements, a fission process occurs, releasing approximately 200 MeVs of energy per U-235 nucleus. That energy creates heat, boiling the water in the vessel. The steam reaction goes up and through a steam line, turning a turbine and creating electrical energy through a generator.
A more detailed thermodynamic cycle is shown here. It is common with a majority of nuclear power plants to have a high pressure and low pressure turbine, as well as a reheat cycle to increase efficiency. Additionally, a demineralizer is added for the steam that comes out of the condenser. And lastly, energy inputs and outputs can be absorbed on the core, turbine, coolant, and pump.
For our following calculations, we assumed parameters typical of a boiling water reactor, including a power rating of 1,000 megawatts, a 33% efficiency, and a 5% enrichment. These assumptions, along with the energy balance equation, allow us to calculate parameters that were useful in solving out our process engineering and economic costs. We ultimately determined that we would generate 3,030 megawatts of heat, with 2,000 of that going to the waste stream, and that we would require 21.2 tons a year of uranium. In addition, equation for energy balances on individual components can be shown to the left.
We want to build our power plant close to a nearby water source. That is why we chose the Ohio River. We also want to build it in an open space and close to our fuel source. The most identified uranium wells in the United States are on the west coast. However, there is a large amount of uranium in Canada, which is much closer. The picture on the right shows many identified wells close to Ohio. There will be a scheduled shutdown of 20 days for scheduled maintenance, and the spent nuclear waste will go to a private company that owns its own repository.
Big risks associated with nuclear power plants involves dealing with spent nuclear fuel. Fission products are taken from the nuclear reaction and stored in spent fuel pools where the fission products are allowed to cool down. After 10 years of storage, they are then taken out and placed in dry cask storages where they are allowed to cool by convection. Additionally, exposure to workers is also a risk, and this can be mitigated by proper PPE.
The life cycle assessment takes a look at the carbon dioxide emissions of a nuclear cycle. The enrichment in the reactor phases contribute the highest doses of CO2, as well as the transportation between different sites. The chart on the left depicts that the nuclear CO2 emissions are 75 times less than that of coal and 4 times less than the closest renewable energy source of solar energy.
The levelized cost of electricity for our project is 9.77 cents per kilowatt hour. We have an estimated total cost and present value of $2.63 billion, including capital costs, operating and maintenance costs, decommissioning costs, and fuel costs. Based on our present value of revenue of around $150 million a year, we predict a payback time on investment of 17.8 years. Similarly, the benefits of this project can be shown in a case study of a 2 gigawatt boiling water reactor plant in Waterford, Connecticut, which hired 1,500 employees and through its resulting activity created 1,000 jobs in the local economy with an estimated benefit of $512 million in benefit to the county. Nuclear reactors are approved by the NEI or NRC prior to their construction. They are granted under a conditional approval license based on a comprehensive design report as well as environmental impact and possible risk analysis. These reactor designs submitted are typically similar to existing approved designs. Our design is very similar to the William H. Zimmer power plant in Moscow, Ohio. Though later converted to a coal-fired power plant, this was originally intended to be a BWR reactor located similarly on the Ohio River with a similar power output and was approved by the NEI and NRC. Likewise, we feel that our design would be approved by the NEI and NRC. In conclusion, our group believes that the Athens nuclear power plant is feasible but presents many concerns. The high capital cost is a serious economic drawback, as well as the concern from the locals in the area over the significant environmental risks involved with the operation of the nuclear power plant as well as the storage of waste. We believe that these are all worthy questions of consideration and should be investigated during the proposal process.
Thank you for your time. Are there any questions?